Hello everybody, and welcome to the Module 3 video for Introduction to Logic. In this module, we'll be covering ambiguity and grouping, and the three subtopics that we will cover are removing ambiguity through grouping, well-formed formulas, and dot notation. Section 2 is technically optional. I think I said it was optional in the book, the stuff about well-formed formulas. So for everything in this section, I think the easiest way to approach it is just look at a bunch of examples and get the gist for how grouping works and how dot notation works, right? If you are confused, even after having looked at a bunch of examples in the textbook and all the examples that I would go over in this video, then you might want to go back and pay close attention to the section on well-formed formulas, but I will be covering it here. I will not, strictly speaking, be testing you on the formal definition of a well-formed formula. However, it's one of those things that you'll have to have at least an intuitive sense of. And I will confess that I myself have an intuitive sense of this. I didn't understand the definition of a well-formed formula when I first was exposed to it. I understand it now, and it's useful. However, again, if it confuses you, the second section of this video, just don't worry too much. You should be able to pick it up from the examples. Okay, real quick, in case you've taken another logic class, or if you're confused by the way in which conjunction and alternation work in our system, there is a difference. So you can ignore this if you've never taken another logic class, or you're not confused by how conjunction and alternation work. In my experience, if this is your first way of being exposed to it, it's not any more confusing than the other way. But if you have taken another logic class, I said in one of the last videos that there's a symbol for conjunction, right? So we would write P and Q, P with this little dot Q, right? Now, we don't have a symbol for conjunction, but that's not the only strange thing. So if we wanted to have three conjuncts together, conjoin three different statements with a conjunction operator, in other systems, you would write something like P dot Q, and then you would need some parentheses, dot R, right? And the same thing goes for alternation, right? So we've seen alternations, P or Q. If we wanted to add another alternation in a different system, if you've taken a logic in community college, we would write P or Q, and then we need parentheses, or R. Now, if you took another logic class and you were paying really close attention, you might know that conjunction and alternation are both, commutative and associative. And what that means is that if we have a schema like P and Q and R, right, that's equivalent to, means the same thing as R and P and Q, right? It also means the same thing as R and Q and P, right? And similarly with alternation, right, if we have P, or in a different systems notation, P or Q or R, right, that's equivalent to R or Q or P, right, or it's also equivalent to Q or P or R, right? So because alternation and conjunction are commutative and associative in our system, we don't need to do this, right? Because we can always sort of vary the internal order in a conjunction or an alternation, and we can break it off into groups kind of whenever we want. So just to save us time, right, we can have conjunctions of, 3, 4 letters, right? That's a legitimate conjunction. Similarly, we can have alternations of as many letters as we want, right? Alternation, And that's just one difference. So there's no need to use parentheses or dots as other systems do here. And this is just a quick tip. If you're coming from another system, this is something that's different. Okay, so part one, ambiguity and grouping. So one of the advantages of our logical language over ordinary English, and one of the reasons why we employ formal logic for various purposes, is that our logical language is such that we can always avoid ambiguity, and we cannot always avoid ambiguity in English. Right, so consider, I'm going to use examples from the book for this section just because I like the examples quite a bit. I don't want to give them up. So consider the sentence, if LeBron leaves the Cavs, again, if he leaves the Cavs again, I will eat a pizza and cry. Right, he did leave the Cavs and I was very upset. Okay, so if we replace the words, the implied if then, right, and the and here for conjunction, we just replace those with the logical operators that we know that they correspond to, right? We get LeBron leaves the Cavs again, arrow, I will eat a pizza, I will cry, right? And we could represent that with the schema, L, therefore P and C. So the problem is that it's not clear exactly in our language yet how we ought to group this. So this could mean two different things based on where we put another set of parentheses. So one possibility, right, is that we want to say this right. Another possibility is that we might want to say lowercase l. Right. So these sentences actually say two different things. The first one, the left one, this one, says that if LeBron leaves the Cavs again, I will eat a pizza, right? And I will cry. So it says that I will cry kind of whether or not LeBron leaves the Cavs again. And I don't think that's what most of you would think that this sentence means in ordinary English, the way that we normally say it. So this sentence over here says that if LeBron leaves the Cavs, right, I will eat a pizza and cry. So whereas over here, right, I'll cry on the left side, it says that I'll cry regardless, and also that if LeBron leaves the Cavs, then I'll eat a pizza. The one on the right says that if LeBron leaves the Cavs, I will both eat a pizza and cry. So the right side one, both my eating a pizza and crying depend upon LeBron leaving the Cavs, right? In the left-hand one, my eating a pizza depends upon LeBron leaving the Cavs. I'll do it if he leaves the Cavs, but my crying does not, right? So this is just kind of an example of how we can use grouping to remove ambiguity. So from a purely logical perspective, both this and this are fine. Both of them are completely unambiguous according to the rules for a well-formed formula that I'll give you in a little bit, right? And I think that based on context and familiarity with the English language, most of you would probably say that the right one is better. But there aren't any absolute rules for how we translate here. So you just kind of have to have a sense of what the operators mean and a sense of kind of what the best translation from English is. I'm never going to punish you very much for reading a sentence with slightly different implied grouping, right? But the important thing kind of isn't what the correct translation is. The important thing is that we make our sentences unambiguous. So if we consider, again, I'm going to use one of the examples from the textbook, right? The schema, P arrow, Q arrow, R, right? Well, we know that the conditional has to have a schema in its antecedent place and a schema in its consequent place. right? And so here we don't know whether or not 1 is should be grouped as P horseshoe or P arrow Q, therefore R, or an alternative way of grouping it would be P arrow Q arrow R, right? So the conditional has to have a definitive, well-defined group on each side, right? It can either be a single letter or some more complex schema, but it has to be a well-defined group. So our initial schema 1 here doesn't have a well-defined group. It's not clear what the structure is. There aren't enough parentheses, right? And you can make it unambiguous in either this way or this way. It doesn't really matter which one. If I give you a question on a test to remove ambiguity, either of these will be acceptable, right? But a conditional has to have a well-defined group on each side, and 1 as written does not, right? So I'm just going to go through a bunch of the examples from the book because I think it's more helpful than the formal definition. So if we look at the second example in the book, P or Q, therefore R, right? So again, this is ambiguous, right? It's not clear whether or not we mean if P or Q, then R. So, and we would represent that like this, right? Or if we mean P or if Q, then R. Right. So both alternation and the material conditional have to have a well-defined group on each side. Every one of our logical operators, except negation, has to have a well-defined group on each side of it, right? And we don't know, based on here, without more parentheses, what exactly the sentence is saying, right? So these are two ways in which we might disambiguate, if that's a real word, or remove ambiguity from this schema. So let's look at another one. That's 3, and that's P if and only if Q, right, or RS. So one convention that we adopt, there's a reason why up here I use the parentheses for this, is that if you see a conjunction of R and S here, you can assume that that is a well-defined group. Any conjunction of single letters is by itself a well-defined group, right? So in our language, we wouldn't need to kind of break apart the R and the S. They stand as one well-defined group, right? But still, this is not completely unambiguous, right? So there are a few different ways that we could do this. I think there are 2, actually. So we could disambiguate this, remove the ambiguity, like P or Q or RS, or P if and only if Q or RS, right? Again, I'm just going through these so you can see a bunch of examples. It's helpful to get an intuitive sense of this. Like I said, there are official rules. I'll give them to you shortly, but I think for most of you, it's easier to just get a sense of this, right? So actually, let's scroll down. So let's look at 4, which is a little more complicated from the chapter examples. So 4 is P and Q, or Q, therefore P or R, right? So there are a bunch of different ways that we could remove ambiguity from this, right? One really easy possibility would just be to make the conditional the main operator. So PQ or Q, therefore P or R, right? So that's one possibility. Another possibility might be PQ or Q, therefore P or R. So the first little segment of this video, I said that kind of a conjunction or an alternation where every component is a well-defined group is perfectly okay, right? So here it's one giant alternation, right? It's an alternation because the main operators are the V's that we use to represent alternation, right? And it's well-defined because every little component is itself kind of well-defined, right? So P and Q is a perfectly legitimate standalone formula. It's unambiguous. If Q then P is a perfectly legitimate standalone schema that's unambiguous, and R by itself is perfectly legitimate on its own, right? What's another way we might do this? I think that gives you a taste of it, how this works. So what I'm going to do in the next section is I'm going to give you kind of the formal way of telling whether or not a schema is well-formed, right? I'm going to give you a formal definition, but again, there are even more examples in the book. I think if you look at them, you'll get a good sense of how this works. You're human beings, not computers, so you're better recognizing patterns than following a formal definition. Okay, moving on to well-formed formula. Okay, so I'm going to give the formal definition for a well-formed formula. This is a reminder to me to remember to project the definitions onto this video with Premiere. Okay, so how this definition works, it's a recursive definition. That means it refers to part of itself, and that confuses people who are not very familiar with math or computer science. So I'm going to kind of talk through the definition, and then I'm going to refer to it to look at some sentences, schemata in our language, and determine whether or not they're well-formed. And all well-formed means is grammatically correct. There's no ambiguity, right? The meaning of everything is clear. All the symbols are arranged according to the rules to give us an actual sentence in our logical language that is perfectly precise. Okay, so the first rule in this recursive definition, or the first part of this definition of a well-formed formula, right, is that lowercase letters on their own, A through Z, right, which stand in for statements, are by themselves well-formed formulas. So things like P or Q or R or S, right? Each of these is by itself a well-formed formula. On its own, it stands in for a sentence, right? And is a kind of grammatically correct schema in our language, right? Pretty simple. So, 2. The second part of our definition is that the negation of any well-formed formula is a well-formed formula, right? So thus far, we have statements that are represented by single letters. If we negate those single letters, so P or not Q or not R or not S, right? Each of those is on its own well-formed formula, right? If you negate any well-formed formula, you get the well-formed formula. Okay. So 3, third component of our definition, right, says that a conditional with a well-formed formula in both the antecedent and consequent place is a well-formed formula, right? And so again, so far, if we look up, we have single letters, negations of single letters, right? So if we have the conditional if P, then Q, right? That's well-formed. We know that single statements are well-formed. We have a conditional that connects two of them. It means that both sides are well-formed, and we're good. So we can also have things like not P, therefore Q, or if not P, then Q, right? That's well-formed because not P is well-formed. It's the negation of a single letter. And Q is well-formed. It's a single letter. So here's where we get into the recursion, right? So we can also have as a legitimate sentence in our language, well-formed, if P then Q, therefore Q, right? So again, this is where the recursion comes in. It might get a little tricky for some of you, but so this whole schema is one big conditional, right? And in its antecedent place, it has another conditional. And that conditional is well-formed, right? Because it has a single letter in its antecedent place and a single letter in its consequent place. The consequent, our big conditional, is this Q over here, right? And we know that that's a well-formed formula because we know that single letters that represent statements are by themselves well-formed, right? And we can get pretty crazy with this at this point. We could have, P, therefore Q, therefore R, therefore S, right? And again, this is well-formed as well, right? The whole thing is one big conditional. It's composed of another big conditional in the antecedent place, right? And the antecedent of that conditional, right, is over here. It's another conditional, but because every single one of our conditionals has on each side of it a well-formed formula, either, another conditional, right, or a single letter, such as, R, S, right? This is well-formed. Okay. Next, we have the rule that states, or the definition that states, that a biconditional with a well-formed formula on each side is a well-formed formula, right? So we have, biconditionals like P if and only if Q, right? Obviously, that's well-formed. By now, you should be getting used to the fact that single statement letters are well-formed, right? If we had, not P if and only if Q, well, that's also well-formed, right? We could also have, P therefore Q if and only if R, right? So this is a well-formed formula. Again, if you understood the definition above for the conditional, right, then you know that this conditional on the left side is itself well-formed. R is well-formed, right? So biconditional that has a well-formed formula on each side is well-formed. We know the whole thing is well-formed, right? And just as, with the conditional, right, we can get really crazy here. We could have, not if P then Q, right? If and only if, Q if and only if P, right? So again, let's just look at this. See, it is a well-formed formula. Let's try to see why. So the left side is well-formed, right? Again, if P then Q, we know by this point is well-formed, right? And we know from our first definition for negation that the negation of any well-formed formula is itself well-formed. And on the right side, we have Q if and only if P. Again, biconditional with a well-formed formula on both sides is itself well-formed, right? So we know that this is well-formed. Okay. So then we get to the rule for conjunction, right? And the rule or definition for conjunction says that a conjunction of any number of well-formed formulas is a well-formed formula. So again, we have the basic examples like P and Q, right? That's well-formed. We can have not P and Q and R. So this whole formula or schema is one big conjunction, right? It's the conjunction of not P and Q and R. And again, because the negation of any well-formed formula is a well-formed formula, that side of the conjunct, perfectly legitimate, well-formed, right? And we can also have, ridiculously complicated ones like P, if P, then Q, if and only if R. Oh wait, that should be brackets. And S, right? If we want to emphasize, we can put a parentheses around there for right now. It's not that big of a deal. We don't need them, but some people like that. So this whole big thing's a conjunction, right? The conjunction operator is kind of hidden right here. We don't write it. And if you look at the previous rules, I'm not going to go through it in detail, but I promise you that this is big and ugly, but it's a well-formed formula. It's an alternation, right? We can see because that gives us this clue. It's an alternation of three different schemata. The first schema that it's an alternation of, this whole thing, is well-formed, right? If P then Q is well-formed, right? RS is well-formed, T is well-formed, and a biconditional that has a well-formed formula on both sides is itself well-formed. So this whole left side here is well-formed, and so the whole thing is well-formed. And that's the recursive definition. Again, I wouldn't panic if that confuses you just yet. Most people, again, when I've taught this class in the past, develop an intuitive sense of this. So there are a ton of examples in Chapter 3. So I would encourage you to go take a look at them. But again, this isn't that bad. Don't be scared by the recursive definition. Okay, moving on to dot notation. Okay, dot notation. So parentheses are nice for reasonably simple schemata. But later on, like in weeks 6, 7, 8, going forward, we'll eventually have to enclose a bunch of things in parentheses inside quantifiers. Don't worry about what that means. But we're going to need a more efficient way of representing grouping than parentheses provide. Again, I'm sure you all are very fond of the parentheses for these very simple formula, and you're going to hate the dot notation that I introduced, but I promise that by the end of the course, you will actually appreciate it. So instead of just using parentheses and brackets for grouping, we are going to use a system that's not very common in logic textbooks, but I quite like, and it is known as a dot notation. And the general idea behind dot notation is that you use dots to indicate grouping. You use more dots to indicate bigger groups. So we're gonna just work through some examples. There is a like perfectly precise algorithmic way to convert between parentheses and dot notation, but it's really confusing. And as much as you might not like looking at this at first, I promise you, if you just do a few of the examples and exercises, it won't be that bad. So how dot notation works, well, let's first consider a schema written in using parentheses for grouping. So this is one of the examples from the book, P and Q, or if R, then S. Right. So again, this should make sense to us. The whole thing's one big conjunction, right? It's a well-formed formula. You can check based on the recursive definition if you really want. So how we convert this into dot notation is first we've got to figure out what the biggest groups are, okay? And what I like to do to make this conversion easier, and this is what I did when I first learned it, is you draw lines under the biggest groups and then the smaller groups, right? So the biggest group is indicated by our brackets here, right? And so we would draw a line under that group. We know that's the biggest component group of the conjunction. The whole statement's a conjunction, right? And then the next biggest group is this if R then S, right? So how the dots work is we use one dot to mark the smallest group, and then 2 dots to mark the next biggest group, 3 dots to mark the next biggest group, and so on. So I'm just going to rewrite this in dot notation so you see what it looks like. So we do P, Q, or if R then S, right? And so I'm going to redraw the lines just so this makes sense. So, right, so this whole group, Q or if R then S, right here that I just drew the line under, right, that's the biggest group in our schema, right, as we see from the line we drew up here in these brackets, right? So we're going to represent that with 2 dots, and then we have a smaller group here, if R then S, which we represent with 1 dot. So the 2 dots and then the 1 dot, right? Let me think of another example real quick. Okay, another really quick example of this is it's not thick enough. 2. So let's do if P, then Q, therefore R, right? So here we only really have one group, right? This if P then Q, right? So if we were to rewrite this, if P then Q dot R, right? Not so bad. You just find the grouping and you put the dot on the right side to make it unambiguous. There probably is a more precise way of telling you how to do this, but it's really confusing. I looked it up once. So just to go through another example, third example, let's do P or if Q, then R, right, with our parentheses. So again, here we only really have one group to worry about, right? And P or dot Q, therefore R, right? And again, we see that same group represented with a dot. Okay, let's just look at a few more of these. So 4, let's try P if and only if Q or RS. So again, here we only really have one major group to worry about, right? And we rewrite it like so. Right. And again, you have to put the dot on on the correct side of the operator to indicate grouping. So this is right, but if we had written this, it'd be wrong. Right. That's confusing. It's ambiguous. Again, you'll get a sense of this if you just look at a few of the examples and try it. Okay, so let's check out something that's a little more complicated. Was that 4? Okay, let's go to 5. Right, and for this one, let's look at the schema. Not Q and R, if and only if Q, then P. Right, so again, this is going to be a little more complicated. So the biggest group that we have is this giant biconditional, right? Then the smaller group that we have to worry about is if Q, then P, right? So rewriting this in dot notation, we get Q double dot R if and only if dot Q, therefore P. Right, and so again, if we redraw the lines to represent grouping, we see that it says the same exact thing, right? So again, let's look at another kind of obnoxiously complicated example, right? So 6. Let's do PQR and PQ or not R and S arrow PS. Right, so again, we can use our line drawing technique to convert between these two, and so we see biggest group, right? Smaller group. So we rewrite this in dot notation, PQR double dot PQ or dot not R and S, therefore PS. Right. Something you will occasionally see me do in the textbook and in lecture is that you can always use more dots to make something clearer, as long as it doesn't screw up the like you have to represent the smallest group with the smallest number of dots, and you have to represent the biggest group with the biggest number of dots, right? But so I will sometimes do stuff like this just to make it easier to read, where I will do 4 dots here just to visually indicate that it's a giant conjunction, right? For especially later on in the textbook, again, even with dots, it gets pretty cumbersome, right? So sometimes I will just use an excessive amount of dots. I always do it correctly in the textbook, so if you see my examples, you get the hang of it. There is one important thing to note, though. If we have a sentence like, if P, then not Q or R, right? We can't really do anything with this to turn it into dot notation. And the reason why is that if we are negating, see this negation sign, a whole group, right, that would be represented in parentheses, right, we have to keep the parentheses. So if we're negating a whole group, like the consequent of this conditional, right, we need to have the negation sign outside of the parentheses, and we keep the parentheses. Same thing if we had a schema like, let's say 8P or not QRS, right? So we can't really do anything with 8 either. 8's already in dot notation. I mean, if we really wanted to be pedantic, put a dot there. it doesn't really change the grouping at all, right? So if we're negating a single big group, then what we have to do is we have to use a negation sign and parentheses. We can't convert either 7 or 8 right here into dot notation. They are as converted as they can get. So we can't get rid of parentheses entirely. We still need them to negate groups. But other than that, I encourage you to just go try the exercises, look at the examples, and I think you'll get the gist of it. I will post a video of me doing all the exercises here with the lines so that you can get a better idea. But again, just give it a shot. It's not that bad, again, especially if you use this line drawing technique. And the ones you have to do right now are not very complicated. Okay. And that is about all that you really need to know for Chapter 3. Again, the important thing is that you go practice the dot notation, that you practice the removing ambiguity stuff. But again, this is not terrifyingly difficult, and I think if you watch the video, look over the chapter, try the exercises, that you'll do fine.